and the universality of black holes.
Okay, so thank you very much for coming here in the morning on the last day of the workshop. Rather than going to a museum, I'm very grateful. And thanks also to the organizers for the awesome workshop, which was really a godsend for me. So, so this is work done in collaboration with my student Shuai Sirui, or Sirui Shuai, who, if you read it in Chinese, the work appeared some half a year ago, and we're working on continuations in various ways. We're gonna get to that in a moment. So let me just briefly summarize the subject of the holographic cone of the holographic entropy cone, which is what this is about, because unfortunately I have a feeling that not everybody feels like they should care about this subject. So I'm going to give a brief maybe one goal for this talk is to make sure that everyone comes out of the room feeling that they should care about the entropy cone. And that's because we'll eventually reach a lot of statements which have definite interpretations. So hopefully you will agree with me that we got some real physical insight out of this. So let me briefly remind us what the holographic entropy cone is about in general. So suppose that I have a holographic boundary, this is it, and here is a bulk. The bulk direction is the vertical direction, and I identify two regions here, which I will call A and B, and I ask what are their entanglement entropies using the Ryuta-Kayanagi formula, and for now we will not be including the quantum corrections. And so, so the answer for A in this picture would be a surface like this, and the answer for B would be a surface like this. But now the question is, what is the entropy of AB? And we have two options. So it's the smaller one of the following two options. One option is the white option, which is just to take the entropies of A and to take the entropy of B and add them together. The other option is a sort of interacting option between these two regions, one where we find a minimal surface which actually connects the regions, and that's, well, this doesn't look terribly different on the, that would be the pink option here, say. And because we are, okay, so that's the, let me call it the pink option. And because we are taking the minimum, there are only two possibilities. Either SAB is equal to SA plus SB, or the other option is the pink one, but the pink one is only activated by the minimum if that thing is smaller than SAB. And so that gives us right away a conclusion that SA plus SB has to be greater than or equal to than the entropy of SAB. So this is subadditivity, and that's a property of quantum mechanics which does not rely on holography, but here's a nice holographic confirmation that it works, or maybe rather a consistency check for the Ryuta-Kayanagi proposal. The entropy cone is built by a very sophisticated or a very powerful generalization of just this type of argument. You consider all possibilities effectively for what the regions are and what their surfaces can be. And just based on the fact that there is a geometry underlying the computation of these entropies, you can generalize this kind of argument to many, many regions and find relations that some set of entropies is necessarily less than or equal than some other set of entropies. So although this inequality is true in general in quantum mechanics, basically all statements of this type, other than subadditivity, that you will derive, will end up being statements which are special to this geometric description. And so the first kind of inequality that you will derive in this way, which is not general in quantum mechanics, but is specific to the Ryuta-Kayanagi proposal, is called the monogamy of mutual information. And the form of it is this. It's greater than or equal to S of A plus S of B. So this is called monogamy of mutual information, and that statement is not true in general in quantum mechanics. It's easy to come up with a counterexample for it. So a counterexample is a GHZ on 4 parties, A, B, C, and some purifier. In that state, every one of these terms is takes an equal value. So 3 terms would have to be greater than or equal to 4 terms. That's a contradiction. I mean, that's just wrong. And so the GHZ set state is an example on 4 parties is an example of why this thing is not a general statement, but a statement only about quantum, about the Rita-Kainagi realizing geometries. And so the way we would interpret this statement is that it's a necessary condition for a quantum state or for the entanglement structure of a quantum state to have a geometric description in the sense of areas, extremal or minimal areas in some underlying geometry. So now you thankfully it wasn't me, but some other people, especially Sergio, who is there online and he was here physically until yesterday, did a lot of work basically applying this kind of reasoning about which surfaces must be smaller than or equal than some other surfaces. They took this to as far as is possible using current computers, I think it's fair to say. And what they came up with, or what Sergio came up with, is the following set of inequalities. So here I have them on the slide prepared for you, if I can display it. Yes. So I hope you will agree with me that this slide, I mean, I hope Sergio there, who is the author of it, will agree with me that this slide is both impressive and disappointing. It's impressive because it's kind of an amazing feat of human thinking that you are able to derive such inequalities, especially number 6 looks really daunting. On the other hand, I think it's fair to say that it's also kind of disappointing in the sense that it's difficult to derive some kind of human insight out of these inequalities. Other than the fact that they are true in the geometry, what are we to make of the fact that these quantities are related in this fashion? And so my goal in this talk is to make some, turn statements like these, not exactly these statements, into and milk them for some real qualitative insight. So the first thing that we're going to do is to change the question slightly. So maybe I'm going to use this board. So the first step is to change the question. And when I say change the question, I mean something very simple. Suppose that you have some number of regions. I will, maybe to stick to the notation that we have on the slide there, I'm going to call those regions A, B, C, and so on. And just to set a little bit of a context, suppose that in total we have distinguished n regions. Okay. There is a I should say one more thing here, which is that the problem of considering a general mixed state for n regions is equivalent to the problem of considering a general pure state or n+1 regions, because you can always just introduce some purifier that purifies the whole thing. And so here I'm going to include a purifier, and in total, I will say that I have m regions in question. This might sound a little tedious. Why did I have to go through this n and m? This is the parameter that's used in all the papers on the archive on this subject, but I think that this one is just far more natural to use in this talk, so I'm going to stick to this one. But m is equal to n+1, and the +1 stands for the purifier. And so suppose that I have distinguished m regions on the boundary, and as a first step, what I'm going to do is to define averages of von Neumann entropies of regions which combine p of those individual regions. So I will use for this the notation S superscript p. So let's just write down what S1 is explicitly. It will be SA plus SB all the way to the last one, which is the entropy of O, divided by the number of regions, which is M. And just to be explicit about this, I'm going to write out the second term in this set of quantities. That will be S of AB plus S of AC, all the way to S of some last region X and O, divided by how many terms do I have here? M choose 2. Yes. And so hopefully you see the definition of the P's average. In some sense, what I'm doing is just taking the data about all these entropies and projecting them onto the trivial representations of the symmetric group. Maybe this is the best way to say what we're talking about here. Okay. And so working with these quantities is what I mean by changing the question. We're not really changing the question, we're specializing to a manageable sector of this question. Okay. So it will be important later. So let's just say, how many such quantities do I have here? And the answer is that this parameter P for these entropies varies between 1, obviously, this is S1, but the maximal value that it takes is m over 2. And in case m is odd, maybe I should put a floor here. And so why is that true? Because we're talking about a pure state, including the purifier. So in a pure state, complementary regions always have equal entropies. So averaging a P region entropy is the same as averaging an m minus P region entropy. They're the same quantity. And so this is the range of my things. So now I have reduced this problem to a problem in an m over 2 dimensional linear space. And the question is, what are the inequalities that bound not the individual entropies, but these averages? There's one more thing that I have to say before going on, which is that there is an easy way to start from these inequalities and obtain inequalities about the averages. And so as an example, we can go back here and do this for monogamy. So suppose that I take this inequality, which is true, but I take it not in the context where I have A, B, C, and 1 purifier, but I take it in a context where I have some m total regions. So what I'm going to do is to apply every permutation on m objects to this inequality, and I'll get lots of other inequalities which will look the same, but will just use different letters. And what happens when I take the average over these permutations? So sum over these permutations on m elements. What I will get is that every one of these terms is going to average to the quantity which has the number of regions that it has. So this will give me an S2 for the average of this term, but actually 3 S2s for the first 3 terms, which is greater than or equal to 3 S1s plus S3. So let me just ask, was that clear to everybody what I just did? Going from a specific inequality to an inequality on these averages. Okay, so if there are any questions, please interrupt me. Okay. So an interesting happens when you apply this procedure to this table. And so that's what I will show you in the next slide. So what happens is that there are 3 of these inequalities, number 5, number 6, and number 7, all average to 1 and the same thing. And so if you're looking for accidents, that would be a pretty amazing accident. If you're looking for regularities, that would be a pretty good hint that there is some kind of regular structure underlying these inequalities. Okay. So the next thing to do is to suppose that, so these inequalities are the full set of inequalities. Sergio proved that fact up to 6 regions or 5 named regions. So m equals 6 in this context has been completely solved at the level of these individual inequalities. So at the level of m equals 6, I have exactly a 3-dimensional space of averages to play with. And so we can actually draw it and look at it in real life. So I have done this exercise for you on the 3-dimensional space of spanned by S1, S2, and S3. And the structure you get is this one. So the green plane, so each one of these inequalities produces a hyperplane, or actually a plane, which cuts this 3-dimensional space into 2 halves, the half which is allowed by the inequality and the one that isn't. And each one of these things we saw before is one such plane. I have 3 independent things, and those 3 things end up producing this plane that you're seeing in front of you. So the one that's colored in this yellowish green is the one that comes from here, and that's the one that comes from symmetrizing subadditivity. The one that comes in this bluish color is the one that comes from symmetrizing this thing, which is our monogamy of mutual information. That's what we have over there. And I just told you that the red things all symmetrize to one and the same plane, and that plane is drawn here in red, and those things make a cone. This is the kind of cone that deserves to be called the cone of average holographic, or the holographic cone of average entropies for now at the level of 6 regions. Are there any questions about how this cone was arrived at? We'll talk about what it means, but are there any questions about how we arrived at it? Yes. Excellent question. I was leaving this out deliberately to check if anybody actually pays attention, because that's the question to ask. And so these other inequalities average to things which are strictly weaker than these 3 inequalities. So they would basically not cut the cone, but they give something that kind of slices outside the cone. Thank you. Anybody else with a question? Okay. So so here's a bunch of statements that, let me see what's next. Okay, so here's a bunch of statements that that I would like to convey to you in this talk. The first statement is that the cone of average entropies, the holographic cone of average entropies, is the simplest it could be. And what does it mean that it's the simplest that it could be? Well, in a 3-dimensional world like this one, where I have 6 regions, so 3 dimensions to play with, the simplest cone would look like this one, because the smallest number of inequalities that I need to actually close a cone is 3. I'm in a 3-dimensional space. So what I mean by the simplest, the cone is the simplest it could be, is that it is a simplicial cone. Namely, the analogous statement holds for an arbitrary number of regions. So if I have 1,000,000 regions, there will be a 500,000 dimensional space, but then I will have exactly 500,000 of these strictest inequalities and no more. That is far from, that's a very non-trivial statement, because that's really far from what happens at the level of these specific inequalities. These specific inequalities bound a space of some number of entropies, but there are way more inequalities than there are dimensions to play with. So that's very far from being a simplicial cone. But the cone of averages is simplicial, and that's the first, hopefully interesting fact that I'm telling you. And we'll interpret this fact physically in a very definite way. Any questions about the statement I just made? Okay, so the first thing is that it's simplicial. The second thing is that, oh, and by the way, I should say this because I didn't make this clear before. But so from now on, everything that up to this slide, everything I told you is known explicitly. But from now, what I'm about to tell you is a conjecture. That's the content of the paper I advertised. So we can talk about how much confidence we have in the correctness of this conjecture afterwards. But for now, please allow me to proceed without actually talking about the evidence. I think that talking about the evidence for it would be distracting at this point, but later we can talk about it. So the first thing is that the cone is simplicial. That's the first part of the conjecture. The second thing is that we know exactly the inequalities that bound this cone. And so the inequalities take the following form. Hopefully you will agree with me that this is also a very simple inequality. It's basically the simplest thing you could hope for in terms of finding regularities in this space. This expression involves a p-1, so obviously it only makes sense when p is greater than or equal to 2. And so I need a special inequality which will complete this cone. The special inequality is just 2s1 is greater than or equal to s2, which comes from subadditivity. So I will call, this one is not of the same form as this, but I will refer to them in this unified fashion. That's the symmetrization of subadditivity. That's the new things. Okay. Let's make a few observations about this inequality. So first, let's consider the case where p equals 2. Do we know this inequality already? And the answer is yes. This thing is the monogamy of mutual information. So this is monogamy. The case of p equals 3, do we know that? And the answer is yes. These are Sergio's 3 scary looking inequalities. So the symmetrization of the things in red is what becomes the p equals 3 case here. And so I will write here V Sergio. And then P equals 4 is where the realm of the conjecture begins. So this is how I would annotate these inequalities. Oh, and actually I have one more observation to make about this, which is, does this inequality remind you of something that you have already seen? And so I'll tell you what it could remind you of. I'm going to write AB plus BC is greater than or equal to B plus ABC. This is this is strong subadditivity. And imagine what happens if this B is a P minus 1 partite region. So B itself doesn't have to be an individual region, but it could be a collection of P minus 1 regions. And now symmetrize that. You will get SP and SP greater than or equal to SP minus 1 plus SP plus 1, right? So if I just didn't have these denominators, this would be the symmetrization of strong subadditivity. And so somehow gravity is telling us that we can drop these denominators and still be true. And it's very interesting to think about what that means. I have a lot of thoughts about that, but maybe for after the talk. Okay, let me erase this part. So if we know the question. Say what?
The inequality that comes from strong subadditivity also falls outside the cone that you're describing?
It is, and actually that fact is already known without even drawing this at the level of this table. Notice that strong subadditivity is not there. The reason why it's not there is that monogamy, the blue one, is strictly stronger than it. So that's why. So it's just true, but it cuts outside the cone. Okay, good. So if we know the inequalities, then we also know the extremal vectors of the cone. And because the cone is simplicial, therefore the extremal vectors and the inequalities will fall in one-to-one correspondence. There's exactly one ray which is opposite a given face in a simplex. Is what I'm saying making sense to you? Okay. So let's talk about the extremal rays of this thing. And you can solve for them. I won't write down a formula for what these, well, actually I will. So maybe this is the best way to present the information about these extremal rays. What I'm going to do is to draw each one of them as a plot. So don't get confused. I'm not drawing this space now. What I'm drawing is a plot of SP as a function of P. So each one of these vectors is a vector in an M/2 dimensional space of these entropies. The various coordinates of this vector, so the values of the SP, can be arranged as an array. And here is just the P which indexes these things, right? Okay. So it turns out that each one of these extremal vectors has a very interesting structure. Oh, and by the way, so the maximal value that it makes sense to go to on this plot is, I just remind you, M/2 floor. This is where the plot kind of ends, yes, or it has to be symmetric this way. And so these extremal vectors have a very interesting structure, which is that they all look in the following way. There is this, and there is this. There is a sharp transition point between two different behaviors. I'm going to call this transition point P bar. And here we have a linear behavior. And here we have a quadratic behavior. So I actually have a plot about this. So maybe I should show it now, which is if you plot these extremal rays, they look like this. And the two plots at the top and at the bottom differ by how they are normalized. You see the vector is an array of various entropies, but there is no God-given normalization for these vectors. So if you're drawing more than one vector on the same plot, you can choose to normalize so that S1 is constant. You can choose to normalize so that the maximal SM/2 is constant, or you can choose to normalize in various ways. So these plots show two different types of normalizations. One of them is where you normalize to a constant value of S1. This is at the top. So So all of these plots begin in the same place, but then they go to various places along the linear plot, and then they'd switch off to a quadratic. Different extremal rays are going to switch from the linear to the quadratic behavior at different points, and I call that thing P bar, the value where the quadratic gives way to the linear. Yes? So I will explain what they are in physical terms in the rest of my talk. That's kind of the main point of the talk. But at this level, how did we arrive at them? We found all of these inequalities, and they are the ones given there in the box. They cut this m over 2-dimensional space every which way. And then I ask, this made a simplex. And what lives on the corner of the simplex? That's what it is. And these corners of the simplex, I just want to remind you, is that they already have they intrinsically have an important meaning, because these are the places where you're almost about to be inconsistent with Ryuta-Kayanagi in this geometric sense. And so these, whatever they are, they must be representing some geometries which are extremal in the sense that even an epsilon deformation would make them inconsistent with Ryuta-Kayanagi at the geometric level. Okay, so I found the extremal vectors, and now I'm trying to tell you about the structure of them. And the structure is that each one of them has some values for these averages, for the S1, S2, S3, and I'm plotting those averages as a function of how many regions you have. And we're finding this behavior. There's the linear behavior and the quadratic behavior. So the fact that I have a linear behavior everywhere, which gives way to quadratic at different places, is illustrated in the top plots here. All of them start linear, but the quadratics pinch off at different, branch off at different places. The fact that all of them have the same quadratic behavior is illustrated at the bottom. At the bottom, I have normalized them differently so that the quadratic is constant, but going from right to left, these various extremal rays switch off to the linear behavior in different places. Is that making sense? I'm looking at Tom to see if this is readable to people. Okay, very good. Okay, so we have the linear behavior and the quadratic behavior. And so this is where we start talking about real physics. So let me just ask you, can you see what the linear and the quadratic behaviors should correspond to in physical terms? And so I will give you the answer that I'm looking for. This I will call PT for perfect tensor, and this I will call EPR, well, for EPR. Okay, so why is that? So what's a property of a perfect tensor state? A property of a perfect tensor state is that if you sometimes if you look at this literature where perfect tensors are used in tensor networks, then the tensor representing, the network, the graphical representation for a perfect tensor typically looks like just a star graph with lots of things. And then we're asking, so what does this thing really mean? It means that the entropy of any p-partite region is going to be given by a minimal cut through this graph. But this minimal cut has a very simple structure. If I take p regions, let's say 3, the minimal cut is just 3. If I take 2 regions, the minimal cut is just 2. And so the perfect tensor has what perfect tensor really means is that entropies of p-partite regions are proportional to p itself. Yes. So SP is proportional to P. And this behavior continues all the way until you cover half the regions. When you go to half the regions, that's when you are allowed to do a phase transition and flip over so that, this SP is really the minimum of P and M minus P. So if you ever thought about perfect tensors, you will recognize the meaning of the linearity of this plot. Did I lose people, or was that clear? Let's talk about this second part of the plot, which is the EPR part. So it's a fair question to ask me at this point, why am I calling it the EPR behavior? Can anyone see why that would be true? So let's write down this quadratic explicitly, because that makes things clear. One thing we know about it is that it has to top off at exactly m over 2. And so the behavior that we have to have here is that SP must be proportional to P times M minus P. Okay. And we will see in a moment that it's the fact that I have these two factors that makes this the EPR behavior. So to see this in more detail, think about what would happen if I had a state which is entirely built of EPR pairs. So I'm going to draw one such state. I'm just going to start drawing lines semi-randomly. So imagine that you have some number of regions, and those regions are connected in a bipartite way, one with another. And then I ask you, what is the value of this quantity SP, the average p-partite region? You may say, I don't know what the average of the p-partite region is, but if you give me a specific region with p-parties, I would know. For instance, if p equals 2 and this is my region, I would just make this minimal cut. And so I would be asking a question of the form, how many lines cross from my p regions to m minus p regions, yes? Now, that's for a specific region, but if I'm asking about the average SP, then I'm asking the same question on average. So the answer is going to be, on average, how many lines cross from a p region to m minus 1 to an m minus p partite region. That means that there must be some quantity which will give me my average in the form p times m minus p times the average population in terms of how many lines I have on any link. And that's how I see this quadratic behavior. Did that make sense to anybody? I see Yiming is appropriately nodding, but did other people get the explanation or no? Okay, so we have the perfect tensor behavior, and we have this EPR behavior. And I think this is already interesting that we're finding these extremal vectors to interpolate between two diametrically opposite types of behavior, but in a very sharp way. And that sharpness thing is this parameter p bar. So if we're looking for slogans, we could say there really are just two types of entanglement underlying these geometries, but we're just interpolating between them in different ways. Are there any questions or comments about that? Yeah. I'm not assuming that they have the same size. This thing doesn't matter, it doesn't care about what the sizes are. Yeah, very good. And that's actually going to become very important that I'm not assuming that, because in a moment we'll be talking about a black hole and lots of Hawking particles. So they're very different sizes for sure. Okay, now let me think about what I should say next before going on. Oh yeah, so it's maybe useful to think about this quadratic and linear behavior in terms of some other bounds. So I'm going to write out one more thing in terms of bounds between different quantities, which is not a new thing, it's just implied by this. And so if you take these inequalities and you add them together in the right way to make a correct, like a convex combination, then you will find the following bound. SP plus 1 over SP is less than or equal to this quantity and this. So I just want to be clear that this thing I just wrote down is not something that's independent of what we talked about. It's just implied by these inequalities. Yes? Okay. So let's think about what this inequality means here. It means that if I give you a specific value of SP, I say the average p-partite entropy is 5 or something like that, you will be able to give me specific bounds on what the maximal and what the minimal p plus 1 partite entropy is. And this minimum and maximum are given by these two quantities. Notice that these inequalities are saturated by this one by the linear behavior, and this one is saturated by the quadratic behavior that we have described a moment ago. Yes, the linear behavior automatically saturates this, and the quadratic one automatically saturates that. So this bound is the perfect tensor bound, in the sense that saturating it gives you this perfect tensor behavior. This is like an EPR type of bound, because saturating this gives you this EPR-like behavior. Was that clear? And so now let's think about what this quantity means. If right now it's written as a ratio, because these entropies don't have a natural normalization. But if I rewrote it in terms of SP plus 1 minus SP, which I could, then that would be an upper bound on the conditional entropy of one extra region given P regions on average. And that conditional entropy further could be turned into a mutual information. I mean, if I subtracted yet again the S1 quantity. The statement about this PT is that you must have exactly 0 mutual information for any region, for any collection of regions up to P+1. Because when you have 0 mutual information, then, well, I mean, mutual information is the entropy of A plus the entropy of B minus the entropy of AB. The only way that I can keep this quantity 0 when this is P partite and this is Q partite is if SPQ is equal to SP plus SQ. That's the linear behavior. So what I'm saying is that there's a if and only if statement between saturating this inequality and saying that there are exactly 0 mutual informations for collections of regions that have up to P+1 constituents. In this sense, 0 is, of course, the minimal value of this mutual information. And so we can say that this inequality tells you that the smallest amount of mutual information is, well, 0 under these conditions. In the same sense, this can be thought of as maximizing that mutual information. It's the smallest value of SP+1 that I can achieve, which means that I am maximizing this quantity. And so on this plot, which I have here, I'm going to erase this word quadratic. The wedge that grows here between the possible linear behavior and the quadratic behavior is about the mutual informations that I'm allowing between various regions. Of course, from our current perspective, we will be tempted to interpret this as a statement about the error correcting capacity of the state as a code. Because every time I have some non-vanishing mutual information, some surfaces which were disjoint at the level of the Ryuta-Kayanagi surface for individual regions will pop up and join. And the region that they joined after popping is the thing that now I can decode, but previously I wasn't able to decode. So whatever thing is happening here is really about the encoding capacity of this of these holographic codes, if you like. And these statements are about the maximal and minimal capacities of these geometric codes. Okay. Any questions or comments about this digression? Okay. So I just told you that I just characterized these extremal rays for you. But what I haven't done is I haven't shown you what geometries actually realize these. This is probably the most, at this point, it should be the most interesting question. I told you there are these are the inequalities that you can, that bound what you can do in the geometric language. But what are the things that are only marginally consistent with that, but are about to fail to be geometric? And so this is the kind of geometry that sits at this extremal ray that makes an extremal ray of the holographic entropy cone. It's almost a perfect tensor state, except that one leg has a different weight from the other legs. Another way to make this geometry would be to take a perfect tensor state on m minus 1 plus w parties. Okay, imagine that I have a perfect tensor on m plus 1 minus w parties, and I just collected w of them together, and I decided I will not distinguish between them. They are now one state instead, one region instead of w regions. So that's the state that you would get then. And the statement is that these guys are exactly those extremal vectors that we talked about. The value of this here, it was characterized in terms of this p bar. So I should give you an equation that relates p bar and w, and the answer is that w is m plus 1 minus 2p bar. And so that's the weight you would put there, given an extremal ray that's characterized by a specific value of p bar. You choose that weight, put it there, and the minimal cuts on that graph are going to give you the entropies that I just told you about. Okay, so first of all, is the assertion clear that this is the the state which realizes the extremality in that cone of averages. Is that statement clear? And what the geometry means at the mechanical level? Yeah, Juan. Here the regions don't have the same size. I'm about to tell you that the W region is like a black hole. So no, it was never assumed. All the ones have the same size. Yeah, that's right. Yeah, all the ones have the same size. It's not about the size of the region. It's about the von Neumann entropy between them. So you could take this thing, and even if it was small and embedded into some larger Hilbert space, that doesn't make. Okay, good. So that's the thing that realizes this. So now I have another pedagogical question, which is, have you seen this picture before? And I mean, I guarantee you that every single one of you has seen this picture before, but can you recognize it for what it is? Exactly, I already said it to Juan, that's right. And so what do we do? Thank you. So what do we do when we study, when Jeff wrote his paper about islands, what did he really do? Yes, he said, I'm going to maybe draw it here. So it's now clear to Juan, and I'm sure it's clear to some of you, but just at the risk of belaboring this point, let me go through it in more detail. So there's a, so what do we have in front of us when we study an evaporating old black hole? There is a black hole which has some area, and then we surround it with some boundary, but outside the boundary is a reservoir where we're capturing this escaping black hole Hawking radiation. And I imagine that some number of particles have been captured in the reservoir, and then when we're and then I'm computing the minimal value of the quantity area plus the bulk entropy for a region that sits between here and that area. And I have two options. I either have the area of this surface, which is almost the horizon, which is close to the horizon surface, or I have, in this case, I have I don't have any bulk entanglement because these EPR pairs are captured outside and not inside the boundary region, inside the bulk. I mean, they're captured outside the bulk and not inside, so this area term is 0. Then the other option is to make the quantum extremal surface 0, in which case I won't have any area contribution, but I will have individual contributions from each one of these particles, and so I will call it m-1 for the individual particles. And that thing, that minimization, is exactly the same kind of minimization that I would have if I was asking about the entropy of all of radiation. I would either have to cut, so these particles are analogous to the radiation, and I would either cut through the radiation part or cut through this term, which is analogous to the area. That's exactly the same trade-off as I have over there. Any questions or comments about that? Yeah, I'm looking at various audience members to gauge if I confused you or not, but is that clear? Is the assertion clear here or no? I need some thumbs up or down from somebody. Oh, Yimin gave me a thumbs up, so I'll continue. So we can ask, what is the reason why these things, oh, okay, so I have a philosophical comment and a real comment. The philosophical comment is that maybe we could have anticipated that the extremal vectors of the entropy cone should have something to do with black holes. Because in starting with this question, we were asking what is barely consistent with a geometric description. So we're looking for states which somehow extremize what gravity can do. And maybe this is a vague intuition, but I would say that, I mean, I think it should be black holes that accomplish that task or answer that question in the affirmative. So maybe we could have anticipated from the start that black hole geometry should be related to the extremal rays. And so that was the philosophical comment. Now the physical question is, why is it true that this relationship, like why should it show up? as in what really is the mechanism behind the fact that that black hole evaporation, as we study it in this island context, like why should it be? Why is it this graph? Maybe let me put it this way. Juan. Yeah.
In the beginning of the talk, you were discussing deriving all of this from the ultra-kinetic prescription. But now you're discussing islands that involve the quantum theory.
Excellent. Yeah. So I have my first reaction to this question is that I agree that it's puzzling, and so here's a. Have you seen this paper? This is Chris Akers and Daniel Harlow and Netta. Sometime after islands were first discussed, they put out this paper about a toy model for the islands, where they discussed these octopus geometries. And they said every time a Hawking particle is expelled, I can think of this Riemann surface as growing an extra leg, or growing an extra puncture, basically. And then they said Hawking evaporation can be thought of as this octopus growing more and more legs, or grow more punctures. This is a geometric picture, which is exactly the same picture as we have over here, yes? And so already at the level of that paper, you could have asked them, why do you think that this geometric toy model makes sense? Because maybe a black hole evaporation is not geometrizable in this sense. So a very stupid answer to your question would be to say, well, this model, to the extent to which this model is okay, we're just following this model. But I think that there is a deeper question here to which I don't know the answer, which is, are we missing something in the islands proposal? Because clearly the process as we're studying right now is geometrizable, but maybe black hole radiation can achieve something that really exploits the quantum extremal surface properties of the quantumness of the extremal surface. So I don't know what the deep answer to your question is. Yeah.
Can these also be realized in vacuum? I thought MMI could be realized in the vacuum state. Is that wrong? It could be saturated in the vacuum state.
Oh, that was like the question of that was what Cesar talked about in his talk. So his talk was let me saturate. He talked about this extensive mutual information. The extensivity of mutual information is the statement that monogamy vanishes. And so he was asking, is there a field theory for which this monogamy inequality is saturated?
What about these extremal rays? Do you really need a black hole, I'm asking, or can you just cook up some in the
Well, I mean, you don't really need a black hole in the sense that I can go to a lab and make a state which has this property and it doesn't have anything to do with black holes. Also, because we're talking about
vacuum on a circle.
On a circle, you will not be able to do it because the circular topology imposes already some relations between these entropies. So the moment you have a circular topology and a single vacuum, you will not saturate pretty much any of these. So actually, yeah, another thing to say is that whatever topology you have on your boundary determine, like it's in some, I mean, I don't think it's worth studying, but in some sense, it limits the possibility of what you can explore in the cone. So this cone is really about all topologies necessarily. Okay, so what I wanted to say in the last 5 minutes is a kind of step back and talk about why this stuff should be related to islands, because it might seem like this connection is somewhat arbitrary. And so I want to go back to Don Page, and when Don Page discussed black hole evaporation in the 90s, he had in mind an idea that I'm going to take one pure state in some very large Hilbert space, and that pure state is going to remain pure at all times. It will describe the whole, the total system, black hole plus the radiation. And the way we deal with, so I'm going to draw this state as a big box. And imagine that this box is filled with lots of particles, like it's filled with little regions. And those little regions are like constituents of the Hilbert space, if that's what I mean by this. And he says this is a pure state, and this state is always going to remain pure. But we have an object called the black hole, and then this black hole maybe initially starts life being pure. So initially this whole thing is the black hole, but now it expels some particles. The whole state is pure, but there is a growing proportion of the state, which I am calling the radiation, and there is a decreasing proportion of the state, which I am calling the black hole. So in some sense, what we have is like a piston, which moves in this direction, and which separates the black hole part from the radiation part. So we always have a pure state, but then we are sliding the division between what we call the black hole and what we call the radiation. I think this is a fair summary of how Don Page envisioned black hole evaporation. And now, why do we have a Page curve? It's because when you take and also he assumed that this state is random. So why do we have a Page curve? Because if you take such a division and for a random state, what you will get is that the entropy of the radiation is equal to the smaller of the two sizes, the size of this or the size of that, the smaller of the two. And so hence, S of R was going to be our Page curve. So, so we have some underlying state, which if we assume is random, is very closely approximated by a very, very large perfect tensor, because a random state is very closely approximated by a perfect tensor. And then we're declaring some subset of this thing to be a black hole. Suppose this is going to be our black hole. Now that construction is exactly the construction of this extremal ray. And so I think these extremal rays had to show here because of this Page-like philosophy that we just have we just have the same global pure state. It's approximately random, so it starts life like the star graph, but then we're declaring some subset of the legs to be bound together in the form of a black hole. Okay, I think that's everything I wanted to say for today, so thank you.
Thanks, Bartek. Then further questions?
Yeah.
So Cassini and Huerta and collaborators have used various combinations of lots of regions to look at C-theorems. And some of them look a bit like symmetrized entropies. I was just wondering if they play any role, if they look like the ones that you're talking about.
I think I don't know that literature, so let's. I'll ask you to show me after.
I have a question. I think I missed. It's a conjecture. This is a conjecture.
Yeah. So it is. I mean,
what evidence do you have?
And so what evidence do we have? So so I told you some of the evidence in passing, which is that when we found that all of these big beasts symmetrized to one and the same thing, that's kind of a hint, and that's hint number one. The fact that when you write this out and you it naturally encompasses monogamy in the same form is also a little bit of a hint. So I'm just giving you hints at how we arrived at it. Then the fact that we found these inequalities, and then we basically found the inequalities by looking at lots of graphs and trying to look for minimal cuts and trying to make some sense out of the patterns that emerge. But then after we found after we decided what the inequalities were, we then discovered that they have this EPR-like interpretation. And I think the EPR-like interpretation is very sensible, because at the end of the day, it's like saying when you're you have some entanglement wedges for p-partite regions, but what when you do in terms of a p+1 partite region, like adjoining one thing, there's always some area, and then you're crossing across that area. Roughly speaking, areas are like bipartite entanglement, and that's what we're finding here. So what I'm giving you here is a vague description of some intuition that can be made more precise, but not at the level of a proof. But basically what this is saying is that areas you always have bipartite entanglement across the area. I think that's the meaning of this fact. So the fact that we landed on the EPR, we're considering a big hint.
So, but I mean, so there's some machinery that people and you worked out to go from Rutakenagi to inequalities or extreme.
Yeah.
So can you use that?
So yeah, let me tell you about that. So so the technology is you have to, so first of all, it doesn't really give you an inequality. It gives you a potential, it can prove for you a guess inequality that you already have. Now here we have some guessed inequalities, so why don't I just prove it? And the answer is that you're looking for some something called a weak homomorphism from a so many dimensional cube to a so many dimensional hypercube. The dimensions of those hypercubes are the numbers of terms in the inequality. So already at the level, the first thing that we conjectured is that P equals 4 inequality. So if you look at these things, I'm looking at 4 partite subsets of at least an 8-party state. That's a lot of subsets, and actually it's 70 of them, I think. So, so we're looking for, in practice, we would be looking for a map at least from a 56-dimensional hypercube to a 70-dimensional hypercube, if I'm not getting these numbers wrong. And that's just not computationally feasible to find one.
Symmetrization doesn't help, but in some
Yeah,
way.
so the most of what we have been doing since like December is trying to find a way to prove the inequality at the symmetrized level without going back to the individual level, and we haven't found it. But we had a strong presumption that there should exist something cleverer for the averages. So we don't know how to do it.
Mhm.
And I'm very happy, but there's an interesting thing which is related to, I'll just say, take 1 or 2 more minutes. There is an interesting thing about this, which is that what we have shown, the standard technique for proving these inequalities involves something called the contraction map that you have to construct. We can see that the contraction map that will prove this inequality, assuming one exists, will necessarily break the symmetry between these terms. And so it's a little reminiscent of replica symmetry breaking in the sense that you have this symmetric statement, but it requires breaking the symmetry to be proven. And so maybe that's a hint that it's actually unlikely that there is some all-powerful symmetrized way of doing this. And your question reminded me of one more thing. So I paused here to say that this is just like strong subadditivity, but with some extra denominators. It's very interesting to think about how those denominators could be brought down from, suppose that you had a holographic proof of strong subadditivity. And then could you just tweak it to bring the denominators down? It sounds like playing with the replica trick appropriately, you might be able to engineer the bringing down of this kind of denominator, basically by rescaling the temperature at the key step of the derivation. So we don't know how to make this statement precise. It's difficult on a variety of practical levels, but I think in spirit, this thing is telling us that there is some kind of extra symmetry that permutes the regions, even though they're different sizes, to reply to Juan's questions. There's some kind of effective replica symmetry between the regions when you're computing the entropy of a p-partite region. And I was very struck by Renato Renner's talk because he was kind of telling us about that, but it's not the same because he was symmetrizing the state, whereas we're symmetrizing the entropies. So the order of symmetrization is different. But some kind of effective symmetry emerges for these calculations.
Okay, more questions for Bartek? If not, let's thank Bartek again.
Thank you very much.